For millennia, humanity has gazed upon the sun with awe and reverence. But what if we could replicate the very process that powers the sun here on Earth? This is the audacious goal of fusion energy research, to create a miniature sun, a controlled thermonuclear reaction that could provide us with a clean, safe, and virtually limitless source of power. Fossil fuels, which power much of our modern world, are finite and contribute to climate change. Nuclear fission, while powerful, produces hazardous waste that poses long-term storage challenges. Imagine a future where power plants are fueled not by coal or uranium, but by isotopes of hydrogen, readily available from seawater. This is the promise of fusion energy, a dream that scientists and engineers have been pursuing for decades. The journey toward this ambitious goal is fraught with challenges, requiring cutting-edge science, engineering marvels, and international collaboration on an unprecedented scale. Yet the potential rewards are so great that the pursuit continues, fueled by the hope of one day harnessing the power of the stars. At the heart of our sun, a remarkable transformation takes place. Under immense pressure and temperatures exceeding millions of degrees Celsius, hydrogen atoms fuse together to form helium, releasing a tremendous amount of energy in the process. Fusion is fundamentally different from nuclear fission, the process used in conventional nuclear power plants. Fission involves splitting heavy atoms like uranium, releasing energy but also producing radioactive byproducts. Fusion, on the other hand, combines light atoms like isotopes of hydrogen, deuterium and tritium, which are abundant in seawater. To achieve fusion on Earth, we need to recreate the extreme conditions found in the sun's core. This involves heating a plasma, a superheated gas in which atoms are stripped of their electrons, to temperatures exceeding 100 million degrees Celsius, several times hotter than the sun's core. Confining and controlling this superheated plasma is one of the key challenges in fusion research. Powerful magnetic fields are used to contain the plasma within a donut-shaped device called a tokamak, preventing it from touching the reactor walls and cooling down. The International Thermonuclear Experimental Reactor, or ITER, currently under construction in southern France, stands as a testament to the global ambition of fusion research. It is a colossal scientific endeavor involving the collaboration of 35 nations, all united by a common goal, to demonstrate the feasibility of fusion power. ITER is designed to be the world's largest and most advanced tokamak, a technological marvel that pushes the boundaries of engineering and scientific understanding. Its massive superconducting magnets, some weighing as much as a Boeing 747, will generate magnetic fields strong enough to confine and control the superheated plasma. The goal of ITER is not to generate electricity, but to serve as a crucial stepping stone towards that ultimate goal. It aims to achieve a fusion energy gain factor of 10, meaning that the fusion reactions within the tokamak will produce 10 times more energy than is required to heat and confine the plasma. ITER is a long-term project with experiments planned to begin in the 20s and full power operation expected in the 30s. The allure of fusion energy lies not only in its sheer power but also in its remarkable environmental and safety advantages. Unlike fossil fuels, fusion does not produce greenhouse gases, offering a path towards a carbon-neutral energy future. Fusion power plants would produce significantly less radioactive waste compared to fission reactors. The primary byproduct of fusion, helium, is an inert gas that poses no environmental threat. While some radioactive waste would be generated by the reactor materials themselves, it would be far less hazardous and have a much shorter half-life than the waste produced by fission. Furthermore, fusion reactions are inherently safe. Unlike fission, which can lead to runaway chain reactions, fusion requires precise and demanding conditions to occur. If any malfunction were to occur, the fusion reaction would simply stop, eliminating the risk of a meltdown. Fusion fuels are abundant and widely available. Deuterium can be extracted from seawater, and tritium can be produced from lithium, a readily available element. While the promise of fusion energy is undeniable, significant challenges remain before it can become a practical reality. The technical hurdles are immense, requiring cutting-edge materials, sophisticated engineering, and a deep understanding of plasma physics. One of the primary challenges is achieving and maintaining the extreme temperatures and pressures required for fusion to occur. The plasma must be heated to millions of degrees Celsius and confined within the tokamak using powerful magnetic fields. This requires superconducting magnets operating at extremely low temperatures, creating demanding engineering challenges. Another significant hurdle is the development of materials that can withstand the intense heat and radiation generated by the fusion reactions. Beyond the technical challenges, fusion energy also faces financial and logistical obstacles. Fusion research is expensive, requiring large-scale investments in research facilities, equipment, and personnel. The journey towards fusion power has been marked by both steady progress and persistent challenges. From the early experimental tokamaks of the 1950s to the construction of ITER, scientists and engineers have made significant strides in understanding and controlling nuclear fusion. The development of powerful magnets, advanced plasma heating systems, and sophisticated control algorithms has brought us closer to achieving the conditions necessary for sustained fusion reactions. New materials, such as silicon carbide composites and high-temperature superconductors, hold promise for withstanding the harsh environment inside a fusion reactor. While ITER is expected to demonstrate the scientific feasibility of fusion power, the timeline for commercial fusion energy remains uncertain. Some startups are pursuing alternative fusion reactor designs such as compact spherical tokamaks and inertial confinement fusion, which could potentially accelerate the path to commercialization. The quest for fusion energy is a testament to human ingenuity and our relentless pursuit of a better future. It is a scientific and engineering grand challenge, driven by the profound potential to transform our world. While significant challenges remain, the progress made in fusion research over the past decades is undeniable. With continued investment, international collaboration, and unwavering determination, we can overcome these hurdles and unlock the promise of fusion power. Imagine a future where the world's energy needs are met by clean, safe, and abundant fusion power. The journey towards this future may be long and arduous, but the potential rewards are immeasurable. The dawn of a new energy era powered by the very heart of the stars may be within our reach.